All right, new problem. Let's say we're trying to find the antiderivatives of x cubed over the square root of x squared plus 1. So, the whole idea of doing trig substitution is to get rid of annoying square roots. So the square root here, it's annoying me. Well, look at our magic trig identities from before that I said would be our guiding light in today's topic. So I'm looking at these trig identities, and I'm saying x squared plus 1. That looks a lot like this trig identity. Tangent squared plus 1 equals secant squared. So you got to say, hey, wouldn't it be great if x was the tangent of theta? If it was, that would be a wonderful thing. If x was the tangent of theta, then look what would happen to that square root there. If you have the square root of x squared plus 1, but instead you have tangent theta there instead of x, you would have this, tangent squared plus 1 under the square root. That would be a great thing. The reason is the square root of tangent squared plus 1 would be the square root of secant squared. The square root of secant squared would be absolute value of secant. So that would be awesome, because if we had tangent squared plus 1 under the radical, we could get rid of the radical. So I want to do this. I want to say, well, let's let x be the tangent of theta. Well, we got to ask, wait a minute, can we do that? I mean, I don't know. This seems like some wizardry here. Well, let's look at the domain of our function. It makes sense to plug in any number for x. If you plug in a number for x and square it, you always get a positive number. You can always take the square root of a positive number. So the domain here is all real numbers. It makes sense to plug in any number in there for x inside that square root. Well, let's look at a graph of tangent. So tangent. Here's a graph of tangent between negative pi over 2 and pi over 2. So remember, we said x could be any number. Well, look at this. The graph of tangent hits all numbers, all real numbers, between negative pi over 2 and pi over 2. What that means is if we choose the right angle theta, the tangent to theta can be our x value, no matter what we pick our x value to be. Like if we pick the x value of 10, we'd say, we have to ask, this tangent to theta, does it ever hit 10? Well, 10, I don't know, that's way up here. Yeah. The tangent to theta is 10 at some point. There is an angle here where if you plug it into tangent to theta does hit 10. So we can always find an angle theta between negative pi over 2 and pi over 2, where x is the tangent of theta. Yeah, so for some angle theta, the tangent to theta will give our x value, no matter what we choose x to be. So we can indeed let x be the tangent of theta for if we choose the correct angle theta. Okay? Well, all right, so let's take derivatives. Dx d theta then, if I take the derivative on both sides, derivative of tangent, secant squared theta. So dx is equal to secant squared theta d theta. All right. So now I can look at my integral here, and I can just start replacing stuff. So x, we're changing x to tangent theta. So the top is going to become tangent cubed. The bottom, x squared plus 1. We're replacing x with tangent theta, so we're going to have tangent squared plus 1. Dx, we are changing dx to secant squared theta, d theta. Now we'll just do some simplifying. All right, so on the bottom there, tangent squared plus 1, it's secant squared. So say, okay, square root of secant squared. It's the absolute value of secant. Now we're in a similar scenario to before. We have absolute value of secant there. That's pretty annoying. We want to be able to cross off secants. But we can't do that yet. We still got that absolute value there. So we got to say, wait a minute. Can we do something about that absolute value? Again, turns out like before, turns out we can just ignore it. So why is that? Well, let's go back to our graph of tangent. Actually, we won't go back to the graph of tangent. We'll just draw the unit circle. So we'll say, okay, absolute value of secant theta. Well, what's going on with that? Well, let's draw the unit circle. So remember, secant is just 1 over cosine. So if we draw some angle theta, we got to say, well, what's going on with its secant value? So cosine is the x-coordinate there on the unit circle. So secant is 1 over that x-coordinate. Well, look back here. Theta is always between negative pi over 2 and pi over 2. Negative pi over 2 to pi over 2. We're working on the right half of the unit circle here. Cosine is always positive on the right half of the unit circle because the x value is always positive on the right half of the unit circle. So wait a minute, cosine's always positive on the right half of the unit circle. But that means secant is always positive on the right half of the unit circle. But wait a minute, then these absolute value bars aren't doing anything. Secant is positive anyway. The absolute value of a positive number is positive. So these absolute value bars here actually aren't necessary at all. So we can just ignore them. Forget about them. And yay! Now we got secant squared on top, secant on the bottom. Can cross off some secants. So now we got tangent cubed secant theta d theta. Aha, now we have a trig integral. We know how to do these. So we'll try to make this look like stuff with secant in it times secant tangent. So I'm going to pull off a tangent. Put that tangent over here. And I say, okay, well, how do I change this so that I have stuff with secant times secant tangent? Well, I'll use a trig identity. So tangent squared. All right, tangent squared plus 1 is secant squared. Well, that means tangent squared is secant squared minus 1. So I'm going to change that tangent squared. I'm going to change it to secant squared theta minus 1. Secant theta, tangent theta. Yay! All right. So now I can do a u substitution. I can let u equal the secant of theta. So du d theta is secant theta tangent theta. So du is secant theta tangent theta d theta. So now let's go back and look at my integral. All right, well, I'm changing u to secant theta, so I'll have u squared minus 1. I'm changing secant tangent. I'm changing that to du. All right, antiderivative u squared, u cubed over 3. Derivative 1 u, got to add my plus c. Now wait a minute, our problem started with x's in it. Can't have u's, so I got to say, well, what's u? U is the secant of theta. So I have secant cubed theta over 3 minus secant of theta plus c. And I still don't have x's in my problem. So here's where we use the triangle trick again. You say, all right, well, x was the tangent of theta, and I want the secant of theta. So x equals the tangent of theta. So think of this as x over 1. The reason why I'm going to do that is because that's the opposite side, and that's the adjacent side in the triangle. So if you draw a triangle, Angle theta. Opposite side is x, adjacent side is 1. Use the Pythagorean theorem. The hypotenuse is the square root of x squared plus 1. Why did I do that? Well, now I can find the secant of theta. The secant of theta is the hypotenuse divided by the adjacent side. It's root x squared plus 1 divided by 1. In other words, it's root x squared plus 1. So, all right, change secant here to root x squared plus 1. So I have root x squared plus 1 cubed all over 3 minus root x squared plus 1 plus c. And there's my answer.